This video is going to cover principles of control selection in case control studies, and it's a pretty big topic, and I'll try and get through it pretty quickly. But as far as just like basic information about case control studies, I did a video. This is just a basic overview, but just to kind of cover the basics again. When you're sampling in a case control study, you have this population. It might be like a roster of the entire town or a sample. Basically, you figure out everyone who's disease positive, set them aside, you're keeping them all. And among those who are disease negative, they're typically bountiful, and it wouldn't be logistically feasible to include them all, so you take a random sample. And then you basically compare the two groups based on their exposure status and see if you're more likely to be exposed as a case, and that would be evidence that the exposure might be causing disease. So how controls are selected is like the part of case control studies that is the most likely to be, like if there was going to be a place where bias was introduced, this is a very, very good candidate. So it's really important to pick a good comparison group. So basically some attributes that a good control group has is that it represents the exposure distribution of the underlying population, and these controls were eligible to have become cases if they had gotten the disease. Basically, if they had gotten the disease, they could have been picked as cases in our study. And when I talk about the underlying population, I'm talking about like this initial crowd, like from before, that gave rise to the disease positive people. They're this base of people that the cases originated from. The controls should also be from that, basically. Okay, so yeah, and controls aren't necessarily healthy, they just don't have the disease of interest. So the first thing I'm going to talk about is the sampling fraction. And so this is addressing that first criteria, that we want the exposure distribution in our control population to resemble that of the population that gave rise to the cases, that underlying source population. And this is achieved when the ratio of like the number of exposed controls in our study to the number of exposed controls in the population at large is equal to the ratio of the number of unexposed controls to the number of unexposed in the source population. So I'm going to show an example with a 2x2 contingency table that will likely make this a little clearer. So here we have our number exposed and unexposed in the source population. So 500 exposed and 1500 unexposed. So I guess this is like a population of 2000. And we also have this disease group and their exposure distribution, and we're hoping that basically the exposure distribution in our disease negative group is reflective of the population at large, because basically the idea is in a perfect world we would have used the entire source population for this study, but we're basically taking a sample, and if our sample is done correctly, it should be as good as using all of them. Basically it should get the same answer. So our sampling fraction, again, number of exposed controls to exposed in the source population, and same with unexposed. If those are equal, basically, then we've done our job, and the distribution of exposure is similar in our disease negative people. So we're using these two cells. So the number of exposed, the number of exposed controls, so 50 here, over the number of exposed in the source population, 500, is that equal to the number of unexposed controls, 150, over the number of unexposed in the source population, 1500? And it is. So that if that's the case, then we would have done our job. This isn't often known. This is more of a conceptual idea to illustrate what we're trying to do, but these numbers aren't often known. So as far as picking controls, there's two basic things to consider. One is when you're picking them temporally, and also this geographic source. So I'm going to go over each of these permutations basically. So for an incidence density case control, if we're using health records from a hospital from 2017 to 2020, we basically, every time whenever a case occurs, we pick a control that's been at risk for the same amount of time. We're basically matching on time at risk. And that's called risk set sampling specifically. So this is our group of people. Let's say we know their disease status, even though it isn't written here. or sorry, we know their exposure status. Everyone is disease negative at this point, and we're not following them in real time. Basically, these are it's like 2022 right now that we're doing the study, and all of this is just historical information in hospital records. So we have these people, we know their exposure status and their disease negative, and we follow them over time. This person outlined in red became a case, and we pick them as a case. And basically, at this time, we pick a control who's been at risk for the same amount of time. And basically, like, what I mean by time at risk is, like, we assume that this group of people all kind of became at risk at the same time. Their exposure status changed or was declared negative or positive at around the same time. So they've all accumulated the same amount of time at risk. So this individual became a case at this time, and we picked a control from that time that we know was at risk for that amount of time and didn't become a case. We continue. No one became a case in this time period. This guy's now a case, and we keep him, and we also pick a control. And yeah, basically we've matched on time, or time at risk. So an alternative would be to sample controls so that the ratio of person time basically in proportion to the person time in the two groups. Yeah, that's a bit more of a nebulous idea, but that's basically what we're ensuring is happening anyway, is that the person time accumulated, like let's just say this is like 20, I don't know, let's say this is like 6 months. We now have 6 months at risk in the case group and 6 months at risk in the control group. Let's say that's another 6 months, or no, let's say now it's like a year. Now we have a year and 6 months of time accumulated in the case group and a year and 6 months of time at risk in the control group. So basically, this is a way to ensure that with risk set sampling, but you can also do that just by making sure the proportion is equivalent. And when you do it this way, when you use incidence density, the odds ratio always estimates the relative risk. And that's great because that's kind of our goal with odds ratios, and that is the case even if the outcome's common. It's also possible that information on cases and controls is collected kind of intermittently, and in that case, a control and a case can be kind of caliper matched on time. I'm going to do a video on matching that will cover a bit about what caliper matching is. But it's a scenario kind of like this. Like, let's just say we have our these 4 individuals who are followed in like 1 year increments over time, and this is basically I'm just recording their status at each year. So no one got the disease. These people weren't measured here, and that's okay, because if they come back into the if they come back into the rotation like this guy did, it doesn't matter. We didn't see them here. We're assuming this is the kind of disease you can only get once. So we can assume they didn't get the disease in this window. Sorry, I got ahead of myself. So yeah, we're following this group over time, and this individual became a case basically in between year 3 and year 4. So basically we find someone that we have data on in that time period, and we can choose them as a case. And it's basically caliper matching because we know their status in this window, and we know that this person began at risk, and we know that presumably they have not gotten the disease, because if they got it here, they'd be disease positive here basically. So we can choose them as a control, and it's basically kind of caliper matching, and it's basically what I'm trying to illustrate is you can caliper match on time, and also it's okay in certain scenarios if the recording of information is sporadic. Also, we could have picked like 2 controls for this case if we wanted, like this. One last, oh yeah, and this is just it continuing again, where this person has like sporadic information, but basically we didn't see them at 2 points, but we saw that we saw them again. We saw they're still disease negative, and yeah, we can be confident that they have been disease negative the whole time up until now. And same with this guy, he's been at risk for the same amount of time, and they grouped them as a case and control pair. One thing that you should plan for, because there's ways of handling this, is that this individual who was chosen as a control for this case, if we continue to follow that person and they go on to become a case, there's a few ways you can handle that. Basically, like, you can choose to treat that as like a separate data point, and now he's a control here, but a case here basically. Yeah, that's one way you could do it. I think there's like some validity issues with that, but basically, yeah, I don't know a ton about how to handle that analytically, but basically that's something you need to uh, plan for, is the idea that someone who is uh, chosen as a control, if they continue to be followed, they might later be a case, basically. Um, so yeah, now just talking about cumulative incidents, that's the other kind of time-based control selection. We have a same scenario, hospital records from 2017 to 2020. Instead of picking a case every time instead of picking a control every time a case occurs, we basically just wait until the end of this time, like study period 2020, and just choose from everyone who didn't become a case. And in this situation, the odds ratio only estimates the relative risk when the disease is really rare, like less than 5% in the population. So here we have this group we're following. That person got the disease. We pick them as a case. That person, get them as a case. Keep going. And these people made it to the end. They were at risk the whole time and made it out without getting the disease. And we basically sample from that, and that's our control group. And that's cumulative incidence. Now we've covered the kind of temporal ways of control selection, geographic in quotes, because it's like the primary one's a little more geographic, but secondary is more conceptual. I'll show you it. It's a little nebulous, but we'll try. So primary and secondary study bases. So regardless of the type of base you're using, there's some things that are supposed to be true. So cases are those who come from the base, and basically controls are those from the base who would have become cases, but they didn't. So a primary study base is like a town. That one's like kind of the one that, like the initial example, I'll come back to it in a second, but it's like an easily defined population that, like, you can probably generate a roster of the people who live in a town in order to enact random selection on, and it's really easy to conceptualize who could have been a case that is not, and they are a control. So controls are simply sampled from this population that gave rise to the cases. And yeah, like a census or tax records might be a way to get that list. So this is basically like an example of a primary study base where we get rid of those people who have the disease. We're keeping them, and now we have this primary study base that gave rise to these cases. All of these people who don't have the disease are essentially potential controls, and yeah, this is the source of controls. It's a little more nebulous with a secondary study base. It's not, well, like, it is a physical place. It's often a referral clinic. That's the classic example of a secondary study base. But it's not necessarily defined by geography, because people can travel to go to it. And controls are those who would have gone to that clinic had they developed the disease, which is sometimes hard to conceptualize. This image might help. So let's say this box here is our referral clinic. And all of these are just basically just people. So cases are those who develop the disease and are referred to the referral clinic. So this person went to the doctor, got diagnosed with the disease, and were basically referred to this clinic, and they are now a case in our study. Same with this person. They got the disease and were referred to the clinic, and they're a case in our study. Controls are those who would be referred if they get the disease, and that's sometimes hard to wrap your head around, because, like, let's just say this is like the best gastroenterologist in the province or something. People might travel pretty far to go to that, and it's hard to say if this person here was to, like, get the disease, would they be referred there or would they be referred elsewhere. It's hard to conceptualize who would go to this referral clinic if they were to get the disease. Like, no, I should have circled that guy. So yeah, like, let's just say this guy gets the disease, and let's say this is a proxy for where people live. This guy lives almost as close to this referral clinic as this one, and if he gets the disease, who knows which one he's going to be referred to. And in that sense, it's hard to say if he's part of this secondary study base. One way to get around that is to use those that are referred to a clinic for other reasons other than the disease of interest. So that if this is like a gastroenterologist, a stomach doctor, and these people have like colon cancer, and this person gets referred for a different disease, not colon cancer, but for some other illness like pancreatic cancer or IBS or something, then it's possible they could be a good control, because we have evidence that if they had colon cancer, they would probably get referred here because they got referred here for something else. So that's probably like where they would have gotten referred if they had gotten the illness. There's some problems with that. Just continuing with that gastroenterologist example, if this is the setting where we're getting our cases and controls, and cases are those with pancreatic cancer, and controls are those without pancreatic cancer who go to that doctor, the choice of controls could have an influence on our odds ratio, because basically, like, let's just say the exposure is like coffee consumption, and these controls are people who have other gastrointestinal illnesses, not pancreatic cancer. It would be like colon cancer, IBS, like I said. And if the risk factor for whatever gave them colon cancer, IBS, is also a risk factor for pancreatic cancer, basically it's going to make the case and control group look more similar with respect to that risk factor. Like, let's just say our cases are getting pancreatic cancer because they drink coffee, and these people are also going to the gastroenterologist because of their IBS or colon cancer, and that coffee is also contributing to that. Our cases and controls will drink a more similar amount of coffee than if we were to use a better control group, basically. And the problem that we're getting down to here is that when we use like this example where this person has another disease and they went to this clinic, that needs to be for reasons unrelated to the exposure we're looking at, is what I'm getting at. Another way that could have gone down is if like a risk factor is coffee consumption and pancreatic cancer. Those who have these other disorders like IBS might limit their caffeine intake. They might limit their coffee intake because their doctor told them to, and in that sense, basically their coffee consumption might be lower than you would expect, and that might basically bias away from the null and make it look like coffee's really causing pancreatic cancer because the controls don't drink coffee. That was a bit of an aside, but basically what I'm getting into is the complications of secondary study bases. I feel like I've never done a case control study, but I would imagine I would probably try to avoid a secondary study base. So some common control sources are things like city registries. So like cities might have like a census or some like, I don't know, like tax records is something that has a list of everyone who lives there, and that might be your source of controls if your primary study base is a city. Neighborhood controls have some value if you match someone on neighborhood, because that usually controls for a variety of factors like socioeconomic status. Hospital controls is another good one, where like if you find a control from the same hospital they were identified from, that can also kind of be matching on geography and so maybe socioeconomic status. If some basically like the socio-demographic structure is richer in some towns and poorer in others, you might be able to control for that. But similar to what I said before, you should make sure that admission for like your controls is unrelated to exposure. Another big one I should have mentioned, I don't think it's not here, is like siblings, where if you're trying to like, I guess that's more of a matching concept, but like if you're you could make your control a sibling for like a twin, where one of them gets some illness and the other doesn't, and you're basically controlling for a whole bunch of like genetic and childhood environment factors.